so this defines a flow. I will call this the flow phi t of a vector field v of x will be just defined by the solution to this differential equation at time t. And this is a flow which is defined, which is correctly defined for all times. So let's say t here belongs to R. So let me say this is the Cauchy problem. I'll call it star. And well, the question is as follows. Can one perturb a little bit V? So let's say perturb V slightly. Just a moment. Let's say I would like to perturb slightly V so that the given point x0 becomes a periodic point. So let's say, so to get a new vector field v tilde, so that x0, a given point, becomes a periodic point for this flow. So let's say x0 is phi v tilde of some time t of x0. Question, can one do this? Can one perturb slightly v to get this v tilde so that a given point becomes a periodic point of the flow? So this is this question has an answer. The answer, of course, depends very much on this word, on the interpretation of the word slightly. What does it mean slightly? So the answer, let's say the generic answer, is given by what is called, now it is a class of statements which are called closing lemmas. Closing lemmas. So the first closing lemma was formulated by Charles Pugh. It's his celebrated Pugh closing lemma in 1967. Well, it says that actually if x0 is a wandering point, if x0 is wandering point for star, then the answer is yes. Then the answer is yes, provided, of course, we interpret correctly the word slightly. So let's say slightly might be interpreted in two ways. So let's say the easy way. Easy way slightly means that, well, I can choose v tilde close to v just in the supremum norm. So let's say that this should be less than some given number epsilon. This is more or less an easy answer, but a very difficult answer is that I can just do this close. So let's say v tilde close to v, not only in supremum norm, but in C1 norm. I even can do this. And this is just really a difficult and, well, it's a really important result. I will just say in a couple of minutes why this is important. But let me first say what is a wandering point, just to recall. So important condition here is x0 should be a wandering point. So let me recall this definition. So let's say x0 is a wandering point of my dynamical system, well, generated by the differential equation star. If let's say if for every neighborhood of x0, let's say open neighborhood of x0, And let's say for every n natural, there exists times t plus less greater or equal than n and t minus less or equal than minus n, and some point x in u, such that phi t plus and t minus v of x belongs to u. So in other words, what does it mean? It means that, well, so let's say x0 is a wandering point. If arbitrarily close to x0, there are other points, x, let's say arbitrarily close to x0, which along its trajectory, once the trajectory goes on, once the time goes on, somehow wanders here, but eventually passes arbitrarily close to x0. Infinitely many times, actually. The same, of course, when the time goes to minus infinity. So let's say if I just consider the reverse trajectory with time going to minus infinity, the same happens. So let's say the trajectory might be wandering somewhere, but then it returns near x infinitely many times. Oh, excuse me, here it should be reversed. So this means that x0 is a non-wandering point. Non-wandering. And maybe I did a mistake. X0 is a non-wandering point here. Surely this should be said a non-wandering point. Excuse me, that was my mistake. Everything I was speaking each time about non-wandering points. So, what are the typical examples of non-wandering points? Of course, let's say examples. So examples are first equilibrium points, of course. But even more than equilibrium points, so let's say points, so for every point z, the omega limit set of z, and so let's say for every z in M, the omega limit set of z is also consists of non-wandering points. So the set of non-wandering points, let me call it, let's say omega of v, will be a set of non-wandering points. So omega of z is a non-wandering point. So let's say belongs to the set of non-wandering points. Omega of z, by definition, just let me recall it, is just the set of all y in n, e in m, which are limit points of the trajectory. So let's say y is a limit in k of phi tk v of z. So the set of all limit points of forward trajectories, so let's say tk go to plus infinity. So the analogous set when tk go to minus infinity is called the alpha limit set. The alpha limit set is the set of all points y in M, which are limit points over k of phi tk v of z, but with tk going to minus infinity. So what we have that both the omega limit set of any trajectory is in the set of non-wandering points, and also the alpha limit set of any point belongs to the same set of non-wandering points. But of course, let's say the non-wandering points contain also may contain something strange, not only equilibrium points or omega limit sets or alpha limit sets of some point. There may be something strange, some strange attractor, for instance. If a trajectory of some point, let's say, goes to some attractor, so there might be something quite strange here, some strange attractor here, which I cannot draw well. Let's say some strange attractor which is not just an omega limit set of a single trajectory, but which consists all of non-wandering points. Well, let me say a couple of words about why this definition of a non-wandering point and when this closing result of Charles Pugh is actually so important. So let's say the most important here is, well, let's say, the difficult result. That is the fact that we can make a given non-wandering point periodic by a C1 small perturbation of the vector field. That is, we can perturb vector field slightly in a supremum norm so that also the derivatives of the vector field also perturb slightly. Well, let us say a toy application of this result, really a toy application, may be considered, for instance, the following Bendixson criterion. So say Bendixson criterion, let's say, for the case when you are considering vector fields in the plane. So let's say V is just a planar vector field from R2 to R2. What it actually says, well, let us suppose that in some, let's say, bounded simply connected region, so let's say this is D is simply connected, and suppose that we know that here the divergence of V is either always strictly positive or always strictly negative. So let's suppose that this is strictly negative. It actually means that, well, through the boundary, the flow goes inside. Well, this says actually that there may be no periodic orbits inside D, because, well, if there is a periodic orbit inside, so if there were a periodic orbit here inside, so this periodic orbit would be enclosing some set omega, and let's say the circulation of this vector field along omega, so let's say the integral of this vector field along omega would be just along the boundary of omega, so along this periodic orbit. So it should be zero, because, let's say, of course, the vector field is always tangent to the boundary of omega. So let's say the flow through the boundary should be zero. So integral over d omega of Vn, let's say, should be zero, where n is just the normal to omega, because V is tangent to, let's say, to every point. But this is actually nothing else than just the integral over omega of the divergence of V. And this should be, of course, well, let's say, this should be, of course, negative. So this cannot happen. This surely is impossible. Which says that actually this situation is impossible. There should be no limit cycle. But now, if once we know that there is no limit cycle, let's consider this condition. That is, the divergence of V is strictly less than zero. Since we are in a bounded set, it means that, and our vector field V is actually smooth, so let's say C1. So it actually means that, let's say, inside D, the divergence of V is less than some constant which is less than 0. And this is a kind of an open condition. That is, if we perturb V slightly, in a C1 norm, then for any perturbation, for any slight perturbation with sufficiently small C1 norm, actually this condition will be satisfied. And this means that actually no, let's say, for no perturbation of V with sufficiently small C1 norm, there might be periodic trajectories, which means actually that there can be no, let's say, all the points except maybe the equilibrium points, they cannot be non-wandering. So they all should be wandering. And this, for instance, says us, if, for instance, we know that in D there is just a single equilibrium point, automatically this says us that all the other points are wandering points, and let's say all their trajectories actually tend to this unique equilibrium point. So this automatically gives us a kind of asymptotic stability of all trajectories entering this bounded simply connected region. So once they enter, they will, at t tending to plus infinity, they will just go to this single equilibrium. This is just a kind of a toy example of what is called, so let's say, what is called autonomous convergence theorems. Autonomous convergence theorems. So let's say this is not really too much interesting because this is an example, a planar example, and we already know that in planar case, while the behavior of the trajectories of a dynamical system cannot be too complicated. But let's say on the same principle, there are important results for n-dimensional systems, which give us conditions similar to this one, that guarantee, for instance, existence and uniqueness of, let's say, a stable equilibrium point and globally asymptotically stable equilibrium point inside some bounded set in an n-dimensional space. So this is just, all this is done principally due to this Pew closing lemma. So before just saying something more here, let's just say that, well, of course, even in this Toyo application, you see that it was important that the let's say that the perturbation here is in C1 norm, because we had to maintain open the condition on the divergence, so the condition which contained derivatives. So in principle, this condition, which is easy, somehow is not too much interesting from the point of view of eventual applications. But it might be interesting, of course. Maybe one can do better. So let's say there is a question. So let me put it in green. So can one substitute here, let's say, C1 by something better, by maybe C2, or even by maybe C infinity? And well, this is still an open question, believed to be quite a hard question. In fact, it was included in 2000. It was included by Steve Smale in the list of mathematical problems for the 21st century. Is problem number 10. So it's problem 10. Well, it's strongly believed that this is impossible. And in principle, while there are results very close to saying that this is impossible, Although there are quite recent results saying that actually for very particular vector fields, for certain classes of Hamiltonian vector fields, this is possible. So in principle, the better you do here, for instance, if you are able to substitute C1 by C2 or CK or C infinity, well, it gives you more room for stability results and for asymptotic stability results like the toy result I just have shown you. Well, this is this was just to say it was story number 1. So let me just try to say story number 2. So let's go further. So story number 2. Oh, let's write it in blank. So let's say story number 2 is again about the same differential equation, y dot is equal to v of y, but it's now the story about controllability. So let's say the first story was somehow dear to the community of dynamical systems people. This one will be dear to the community of control people. So we have here, let's say, y of 0 is some given point, say x0, and there is another given point, say x1. And I would like to ask, is it possible to add something here? Let's say add some plus small u of t with maybe, well, u of t just small in C infinity norm. So let's say in the uniform norm, so less than a given epsilon, so that y at some point t becomes x1. So this is just a typical controllability problem. While the u of t is called the control function steering the initial datum x0 to the final point x1. So a couple of years ago, I just heard this story at the geometric seminar at St. Petersburg, at Alexandrov geometry seminar. This was a story by Burago, Ivanov, and Novikov. They interpreted it in the following way. So let's suppose that you have a small fish. So there is a small fish here that actually floats in the sea, and initially it's in the position x0. So a fish is just one dot. So it's in the position x0, and while v is just the velocity of the sea, it may be as high as you like. But it's just bounded and smooth. So let's say it's globally Lipschitz, it's globally smooth, and it's globally bounded. And so as usual, v, let's say v is globally bounded, and let's say v is globally Lipschitz. And then the fish can just move arbitrarily, but its own velocity cannot be more than epsilon. It's quite weak, so its velocity may be very small, and the velocity, the c, say the maximum velocity of the water might be very high. So question, can the fish reach some given point x1? So can one choose this u of t so as to reach this velocity x1? This point x1. Of course, to say yes, of course, there are some natural conditions to satisfy. First of all, well, this is the water. So since the sea is made of water, so we can say that the water is incompressible. That is the divergence. The divergence of v is 0. That's condition number 1. And the second condition, it's also quite clear that even with the divergence of v equal to 0, it's clear that, for instance, a v which is constant, but it's just, let's say, shifting everything just in a single direction, constant going in just one direction, but with a very big constant. So, for instance, if x0 is here and x1 is here, of course I cannot go in the opposite direction to the flow. There is no way to do so. Well, then there is a second condition which appears to be actually necessary. They call it vanishing mean drift. Vanishing mean drift. And well, vanishing mean drift actually means that if you make an average of this vector field over very big balls, let's say over balls of very big radius, or over, let's say, cubes of very big side lengths, well, make an average. So if R becomes very large, this goes to 0. So it means that somewhere the velocities of the water may be very high, that there may be storms preventing the fish to go in some direction. But in the average, on very large scales, let's say the sea is not too stormy. So over very large scales, the average velocity of water is quite small. And well, it happened actually that these two conditions actually gives a possibility to answer the question about controllability. That is, the answer is positive. Under these two conditions, let's say the theorem by Burago, Novikov, Burago, Ivanov, and Novikov says that 1 plus 2 implies yes. So the fish might go from any point to any other point. Well, there was this very nice argument they used. Actually, the argument is maybe, well, if you just separate the argument from the technical part of it, the argument itself is just half a page. It said something like this: suppose that you cannot reach from x0 your point x1. So it actually means that your reachable set somehow is not containing x1. Let's suppose, just for the sake of simplicity, that is bounded. What does it mean? It means that you can arrive from x0 everywhere here, to this point or to this point, or even to this boundary, but you cannot arrive outside of the boundary. Why can it happen? It only can happen if the velocity field here at the boundary pushes you inside. It means that the velocity field in the boundary pushes you inside, and it is sufficiently strong to push you inside. What does it mean? Your own velocity might be epsilon. You can choose its direction. It means that the part of the velocity v which pushes you inside, so the part along the inner normal of the velocity field E, should be a little, at least epsilon. So let's say v, let's say multiplied by external normal. This should be, let's say, at least, it should be at least minus epsilon. This actually means that the flow of your vector field along this boundary should be negative, which is impossible because the divergence of v is 0, because the flow through this boundary is actually the integral of the divergence over this reachable set. So this is just, that is the nice argument. Of course, this argument needs something technical. You need just to say, well, why you can just integrate over the boundary. So they needed to show that the boundary of a reachable set is actually rectifiable. And of course, you have to deal somehow not only with bounded sets, but the heart of the argument is this one. But let me note here two things, or maybe three things. So, thing number one, that this theorem actually, at least this argument actually implies, well, it inherently implies that x1 should be different from x0. But if I just think about story number one, so there should be some connection between story number two and story number one, because let's say the story number two about making x0 periodic is again very similar to story number two. It's like saying that, well, let's say taking x1 equal to x0. But, well, let's say this technique of Burago, Ivanov, and Novikov will not allow this. This is number one. Number two, of course, if I would like to show some kind of a, let's say, some analog of the Pew closing lemma, but now not for non-wandering points, but for just for any point x0, well, I would need here not just u of t, but I need here something like, let me say it, u tilde of y of t. So this is much stronger controllability question. So I'm asking now not just about controllability, not just choosing a control depending only on time, but choosing a control u tilde which depends on the position of my fish. So this is somehow stronger. And actually, what we did together with Sergei Kryzhevich from St. Petersburg a couple of years ago, we just managed to answer actually the question, and quite constructively answer the question. Let's say, consider here x1 is equal to x0. But now I don't know anything about x0. X0 may be a wandering point or maybe a non-wandering point. So let's say maybe may not belong to omega v. Example, the classical example is as follows. Let's say, suppose that, let's say n is equal to 2, and let's say v of x1, x2 is just, say, suppose, well, some big number, let's say n sine of x2, 0. So it actually means that my flow is like this. So there are, okay, of course, there are trajectories which remain stationary. So let's say these are stationary points. So all these lines are stationary points, actually. But here you have, let's say, all the flow is to the right, all the flow is to the left. Here is all the flow is to the right, here all the flow is to the left. So this one is x1, this one is x2. It means that except the points on the lines which consist of only of stationary points, so let's say except for the points on the lines x2 is equal to k pi, where k is any integer, except of those points, all the other points are wandering points. Let's say they are not belonging to omega v. So let's say omega v is just x such that x equal to x1, x2, such that x2 is equal to kp. But I'm asking, is it possible to make, for instance, even this point, which is not non-wandering, can I make it? Can I make it periodic? And well, our answer was yes, quite a constructive. So we managed to make an exact perturbation u tilde depending only on y, u tilde of y, which is, let's say, very small, not only in C, but only even in C1 norm. such that, let's say very small, such that with this perturbation, any given point becomes a periodic point. So let's say this one becomes a periodic trajectory. Well, our observation actually says that in this case, we have a kind of a very strong analog of the Pugh closing lemma for S, so that this means that every point, so the theorem was 1 plus 2 means every x0 can be made periodic by a C1 small perturbation of the initial vector field V. But the observation is, can one then repeat the same argument while to solve also the initial problem by Burago, Novikov, and Ivanov, that is, to solve the controllability problem, but now in a constructive way, because let's say the argument of the original argument of Burago, Novikov, and Ivanov was quite non-constructive. They said to a fish, well, you can just reach from this given point x0, you can reach this point x1. So you can, but how? They didn't say. So the argument was just a contradiction argument. If you cannot reach, then something happens and you have a contradiction. And well, now actually our answer was, let's say, partially one can do better. One can even say that there is a control depending only on the position, not only of t. So let's say you can say that you can take a control u tilde is equal u tilde of y. But again, this control was non-constructive. The main idea was using the following, let's say, curious observation, maybe a lemma. That is, let's say, if the flow phi t of v has some invariant measure, mu, and then from any x0 belonging to the support of this measure, you can reach any x1 in the same connected component of the support of mu. This is not very difficult to prove, but let's say the basic idea of the proof is very non-constructive. One uses, well, let's say, this connectedness condition, connected component, just to say that the set of points you can reach from x0 is closed in the support, but it's also open in the relative topology of the support, so that should be connected. And somehow this is quite non-constructive. So question, can you do it in a constructive way? And now let's say the answer is yes. Let me now give you a constructive answer. So let's say, suppose you have your x0 and x1. Your fish is now here in x0 at point 0, and you want to reach x1. So what you do, you just connect x0 with x1 by any curve you would like more or less frequently to follow. Not that you follow just this curve, but you will just visit it frequently. What you now can say is that, well, any point of this curve can be made periodic by some small perturbation. So let's say I can just perturb my V in a constructive and a small way so that every point can become periodic. So let's say under this perturbation, this point will become periodic. Maybe I can just also make this point periodic. So What does it mean? Well, let us look at the following simple observation. Let's suppose that now you can start from some point, let's say point A at time t0, let's say, so that u of, let's say, at time 0, for instance. You are in the point A, and suppose that you are able to reach some point B. Suppose that at some time y of s is another point B. So you are able somehow to reach from a point A B. What else can you reach? Well, I would say that you're able to reach a small ball around B. Let's say you're able to reach a small ball of radius rho around B. You can reach it at A. How? Starting from A. How do you do this? Well, if you're able to reach from A, B, you first start following the trajectory from A to B. So if you follow it for all the time from 0 to S, you will arrive to B. But now if you would like to arrive here, okay, let me write it in, let me put it in red. If you would like to arrive here, what you do at some time before S, so let's say at some time, it will be time S minus some tau, and all the parameters here you can just constructively estimate, the parameter rho, the parameter tau, and so on. You stop following this curve. You just direct yourself directly towards this point. You just follow the velocity field, which is a velocity field at this vector B, So let's say you will follow, let's say, the velocity field at a vector B plus some small constant. And this constant, of course, depends on the point where you would like to arrive. So this actually means that, well, if you are able to arrive from a point A to point B, then you are actually able to arrive to all the ball near the point B. But now let's again consider our problem of arriving from point x0 to point x1. Now we have that every point of this artificial curve, which is not a trajectory at all, but just an artificial curve I have drawn here, can be made periodic. So let's say every point here may be reached at some time from itself. It actually means that the whole ball around every point can actually be reached at some time from this point. And even if you think even more, every point in each such ball, every point can be reached at finite time from any point of this ball. So let's say you can do like this. So you can just, for every ball, you can find constructively a trajectory which more or less follows the periodic trajectory, but then just at some time shifts from the periodic trajectory and gives and arrives to the given point. So what you can just now do, you can just, well, this is for every point in your curve. Now you can just cover your curve with such balls. And since your curve is compact, you just find a finite number of such balls. And actually, what you say is that you are able to find a finite number of balls. So let me write it again. So this is your trajectory from x0 to x1. Excuse me, the curve, the artificial curve. So you just cover this by a finite number of balls. And for every ball, you're able constructively to reach each point from the other point. So what you do, you first reach from the initial point some given point at this ball, which is in the intersection with the second ball. Now, once you arrive at the second ball, you constructively make another trajectory which reaches the given point in the second ball, which is in the intersection with the second ball, and so on, until you arrive, of course, at point X. So how your control would look like? So your control actually, it means actually that you are constructing a control like this. Y dot is V of Y plus now U on both Y of T and also of T. So what you do, so maybe it's better to show several different instances of time. So let's say first, I have this artificial curve. I'm starting at x0. I would like to arrive at x1. So first, you consider the first ball here. I make this point periodic by a small perturbation. And now I follow this periodic trajectory. At some time, I shift from this periodic trajectory and arrive to this point. Now, once I arrive to this point, I'm here. So let's say this given point is in the second ball. I'm making this point periodic at a certain, and I'm following this periodic trajectory. So I just shift another control. I switch another control here. And at a certain point, I'm just shifting from my trajectory and going to this point. So in this way, I will be arriving to the point x1. What is even probably more interesting, sometimes in applications, people ask themselves about the following problem. Now, suppose we have not a single fish, but a storm of fish. Let's say, so let's see, you have several fish. So a fish here. A fish here. And the fish here. And they would like to arrive at the respective positions. So let's say here, 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 and here. Can you do it simultaneously by a single control? So can you just move with a single control? So you have to make your control. So you have to make your control U, which depends probably on the position and on time t, so that at time t to 0, so they all start at t equal to 0, they are all here. At t equal to t, they should be all here. What you can do, you can just repeat the same argument for just, well, a finite number of arcs connecting the points. So again, let's say the situation is a little bit more complicated because you divide it in several, well, let's say you cover curve in some finite number of pieces, and you make simultaneously let's say the first balls periodic. There is some technical argument which allows you to do this. While you choose let's say your periods so large that more or less at almost the same time you arrive very close to, let's say the first fish arrives very close to this point, the second fish to this point, let's say the last fish to this point. And almost simultaneously, you just shift from those trajectories and go further. Once you arrived here, you add the small perturbation so as to make the second points all periodic, and you continue in such a way inductively until all the storm of fish, or let's say school of fish, arrives to the same destination. So now let me say that there are several challenges here. Several challenges here are as follows, just to finish the story. So challenges. first. Well, probably 0. Let's say the stupid question, can you make u is equal to u of t, of just t? Well, once you would like to do it with a single fish, of course, this is possible. But let's say, because, well, let's say it's the same as saying u is equal to u of a position and t, because once you have chosen a single trajectory, you already fixed the value of y of t. But if you would like to do it for several fish, for several school of fish simultaneously, then this is impossible. The second thing, can you make u depending only on y? And the answer is yes. This is quite an interesting argument. The answer is yes. At least once you ask yourself that the supremum norm of u is sufficiently small. But the more interesting challenge would be as follows. Can you say, well, can you choose u depending only on the position, but so that you choose u small not only in supremum norm, but also in C1 norm? But I would say probably yes, but the answer, well, seems to be for the moment quite difficult. And of course, if you are able to do so, there are quite interesting applications of this technique that would go far beyond the optimal control. But this seems to be quite a serious challenge and quite a difficult question. So let me probably stop here and ask you if there are some questions here. So Control H. Okay, so let me finish here. Are there any questions?
Eugene, just one question. You were constructing your path using balls of a given radius, yes?
Yeah.
And you need an estimate on the radius to be fixed in order to cover in a finite step the path.
Yeah, sorry, I have
You have many paths. You have to impose some strong separation with respect to the radius of these balls in order not to have self-intersections.
Once you are speaking about a single trajectory, this is not a problem, because I'm just switching each control in a new moment of time.
Yes,
so
when you have more than one fish.
When I have more than one fish, this is quite complicated. So I have to make the trajectory somehow quite far away from each other, so as to be able to do the job. Yeah, that's quite complicated. Yes, that's
okay.
Geometrically, you have somehow to avoid self-intersection. Of course, if you would like, let's say your control to be dependent only on anyhow, let's say because, well, in principle there is no problem of self-intersection at different instance of time, but if you would like to make them, let's say, move in a certain ways synchronously, then of course you have to avoid self-intersections. Yes.
Okay, thank you.
I have a question. I'm Enrico. Just to understand, when you were talking about the argument of Ivanov, Burago, and Novikov, you said that it was important that x1 was different than x0. But if you can take them differently, if you can steer x0 to x1, then you can also steer x1 to x0, and then you can take them the same.
Yeah, sure. Yeah. I just say that the original, but let's say the proof itself, of course, yes. let's say this. That's true. But this doesn't come directly, so to say, that doesn't come directly from the technique of the proof. Yeah. Oh, excuse me. Are you saying something?
No, I just have the kids at home.
Okay.
Okay. Are there any more questions? If not, let us.
Maria Stella, just,
sorry.
I mean, thank you to Eugene. I don't understand why, when you, along this curve joining the target point with the starting point, when you modify the fields to make a fixed periodic orbit, you again forward meet this curve from
I'm just imposing, so let's say I'm imposing my controls so as to arrive to the next center of the next ball.
This is stable for small perturbation, this property of the curve.
Yeah, I'm not just following all the curve. I'm just following quite frequently the points on the curve. While my trajectory would be quite strange. I'm just going to a point on a curve, first making maybe a very long turn, almost periodic turn.
And you guarantee that go forward toward x1, however.
Yes, I'm each time I'm just going to the next position. Yes.
Okay. It's not so obvious for me, at least. Thank you.
Okay. More questions? If not, let us thank Eugene again. And I can say that may I say that you will find this conference on the YouTube. Sorry, I didn't ask for the permission to record this conference, but at the moment this has been done, and will be available on the usual YouTube channel from Department of Mathematics in Pisa. Okay, see you next week for the seminar by Carlo Mantegazza, and thanks again to Eugene.
Okay, thank you. Thank you. Bye.
Bye.
Thank you.
Bye-bye.
Bye.
How do you